You will find this particularly complex right now, but when we go and study individual turbomachinery models, we will cover the theory, which will answer a lot of your doubts. So we will see the first model among the moving reference frame approach is the single reference frame model. A moving reference frame is defined within the model of a single fluid domain. So we'll take an example of this particular rotating component, which is, let us say, rotating in the clockwise direction. These are the 4 blades of the impeller, and this is the surrounding domain, which is this particular domain. So this is rotating, this particular set of blades is rotating in clockwise direction with some RPM. So what are we going to do is that a moving reference frame is defined within the model of a single fluid domain. So all this area basically consists of fluid. All this area is going to consist of fluid. In this, so what will happen is that the entire domain is moving with the frame speed around the axis of rotation. Axis of rotation is defined across this point. Stationary boundaries form a surface of revolution. So this particular black surface is the stationary surface, which is forming the surface of revolution around the moving domain. This moving frame takes care of the rotational effects of the blades. So instead of actually solving rotation of the blades, we are just going to solve a steady state equation having the rotational effect. So we are going to have a domain which moves with a frame speed around the axis of rotation. We are going to have stationary boundaries which form surface of revolution, and the moving frame takes care of rotational effects of the blades. So this is referred to as the single reference frame model. Next, we have the multiple reference frame or frozen rotor stator approach. In this, the only difference is of the earlier concept, we have sort of 4 baffles. One is here, second is here, third is here, and fourth is here. These are fixed. These are baffles. So now we do not have a surface of revolution of this because this is fixed. All these 4 are fixed. This is used when there is stationary component which cannot be modeled as surface of revolution. So this multiple reference frame approach is used when we cannot model the fixed surface or stationary components as surface of revolutions. So in this problem we use 2 distinct domains which are considered. One is the moving frame and the other is stationary. So this is particularly stationary, all this, and this particular enclosed by the dotted line is considered as the moving reference or the moving domain. An interface is defined between the stationary and the rotating fluid zone. So this is called as the interface, this dotted line. Velocity vector and velocity gradients are then transformed at this interface. Flux, momentum, and energy and other scalars are exchanged at this interface boundary, and there is no relative motion between the domains. So there is no actual motion of this particular inner domain. Still everything is stationary, everything appears to be stationary, but the rotational effects are considered. The third model that we are going to review in this particular session is the sliding mesh approach or sliding mesh model. In this, the domain is divided into rotating and non-rotating zones. So we are going to consider the same problem that we considered in the earlier example, having 4 bladed impeller rotating around this axis of rotation. There are 4 baffles which are stationary, and there is an interface which is the surface of revolution. But what is the difference in this? Is that the interface is modeled as a non-conformal surface of revolution, and in this approach there is relative motion between this stationary and this moving domain. So this particular blades are actually rotating in this particular approach, and the outer zone is stationary. So the interface is modeled as a non-conformal interface, and there is actually in the model itself, in the CFD model itself, there is relative motion between the zones. The mesh is moved during each time step, and fluxes are then modeled or transferred at the sliding or moving interfaces. So there is actual motion only in this approach. There is the CFD model is actually rotating. So to summarize this particular session, this was your introduction to the turbomachinery application of CFD. And in this particular session, we saw highlights of what are turbomachinery, how they work. We also saw how CFD is applied to turbomachinery, and what are the different approach when we model turbomachinery using CFD. In the latter sessions, we are going to see each model in detail now, and we are going to see how to set up the individual models, that is single reference frame, multiple reference frame, as well as the sliding mesh model within the Fluent software, so that you are ready to start your own turbomachinery flow CFD project. Thank you for attending this session. See you in the next session of this course on turbomachinery flow model using Fluent software.